In Objective 5, we'll learn how to solve exponential equations, which are equations that have variables in the exponent. When solving an exponential equation, the goal is to use some of the properties that we've studied so far in order to remove the variable from the exponent, which would make us be able to solve for that variable then. There are a couple different techniques to do that, and we'll talk about them one by one. The first one is to take the natural log of both sides of the equation. Just like you can take the square root of both sides of an equation or add 2 to both sides of the equation, I can take the natural log of both sides of the equations and write that ln of e to the x plus 1 is equal to the ln of 4. Now what I'm going to do is use my cancellation properties here. I actually have ln of e to the x plus 1, and my cancellation properties of natural logs and exponentials say that those will undo each other, and I will be left with x plus 1 is equal to the ln of 4. The last thing to do to get x by itself is to subtract 1 from both sides, and I'll get that x equals the ln of 4 minus 1. And that's going to be my final answer. What I'm not going to do is say that this is the same thing as the ln of 3. That 4 is really stuck inside that natural log, and so the 4 and the 1 cannot be subtracted. Remember, the ln of 4 is actually a number of itself that then we want to subtract 1 from. This one worked really nicely because the base of my exponential equation was e, but this technique will also work when my base is a different number. Let's go ahead and try it. In b, I will still take the natural log of both sides. But unfortunately now, I'm not going to be able to do that cancellation property. I have the natural log of 5 to the 3x minus 1, not the natural log of e to the 3x minus 1. So instead of using that cancellation property, I can try to use a different technique, being our log law 3, the one that turns exponents into a multiplier out in front. So I can go ahead and write this as 3x minus 1 all times the natural log of 5 is equal to the natural log of 4. It is really important to make sure that you put those parentheses here, otherwise you might think it's just the 1 that's getting multiplied by the natural log of 5, but it's this whole quantity. Now I want to start solving for x, and I see that x is glued through multiplication with this 3, and then there's some addition gluing it with this minus 1, and some multiplication with this. And I want to peel back these layers one by one. The first thing that I'm going to do is undo this ln of 5 multiplication by dividing both sides by the natural log of 5. And I'll get that 3x minus 1 is equal to the natural log of 4 over the natural log of 5. Then I'll go ahead and add 1 to both sides of the equation and get that 3x is equal to the ln of 4 over the ln of 5 plus 1. And lastly, I'll divide both sides by 3. When I do that, it'll put a 3 in every single denominator. So it'll look something like this. I'll get that x is equal to the ln of 4 over 3 ln of 5 plus 1/3. So this technique of taking the natural log of both sides of the equation is a really great technique whenever we have an exponential equal to a number. So there's just one exponential piece in my equation. This technique actually can work in other cases, but there's usually a better technique to use. But in order to introduce that, let me try this problem with the same technique. I'm going to take my exponential equation here, and I'm going to take the natural log of both sides of the equation. When I do that, I'll get the ln of 4 to the x squared power is equal to the natural log of 4 to the 6x plus 7 power. And just like the very last question we did here, I'm going to be able to use my third law of logarithms to bring this down in front. And I would get x squared times the natural log of 4 is equal to 6x plus 7 times the natural log of 4. Curiously, on both sides of the equation here, I have a natural log of 4, and so I can go ahead and divide both sides by ln of 4 to just get rid of it all together, leaving me with x squared equals 6x plus 7. Now that I'm here, I'm going to go ahead and pause and try to make an observation. When I started this, I had the equation 4 to the x squared is equal to 4 to the 6x plus 7. And now I'm to the point of x squared equals 6x plus 7. And it looks like I ended up just being able to equate those powers. And I think that actually makes some sense. If I have 4 raised to a power, and that's going to be equal to 4 raised to a different power, well, then the powers themselves had to have been the same. So now this is our new technique. If I have an equation with two exponentials in it and both sides have the same base, then I can actually just equate the exponents and say x squared is equal to 6x plus 7. So moving forward, we can just jump right to here. All right, now we need to finish solving this. Whether we did this whole process with natural logs or you just jump to equating the exponents, I need to solve the quadratic equation x squared equals 6x plus 7. In order to solve a quadratic equation, I like to move everything to one side of the equation, and I think I'm going to be able to solve this with factoring if I make this x minus 7 and x plus 1. Then if I use that zero product property, I'll get that x minus 7 is equal to 0 and x plus 1 is equal to 0, giving me a solution set of 7 and negative 1. All right, let's try this in B. Here I have 5 to the x minus 1 is equal to 25 to the x. And looking at this, I have exponents on both sides, and so I am really tempted to just equate those exponents and make it x minus 1 is equal to x. Unfortunately, though, I can't do that, and do you see why? It's because my bases aren't the same. I have 5 to the x minus 1 is equal to 25 to the x, and since those bases aren't the same, I don't know that those exponents have to be the same. Here's what we can do, though. If I notice something special about these bases, I have 5 on one side and I have 25 on the other, and I know that 25 is the same thing as 5 squared. And I wonder if I can use that fact to rewrite this so that I actually have the same bases. Let me show you what I mean. I'm going to keep the left side the same, but on the right, instead of saying 25, I'm going to say 5 squared and then raise that to the x power. Now I still am not quite where I want to be because I have base to a power equal to base to a power to a power, and that's a little different than what we saw in the previous example. So what I need to do is somehow resolve this power to a power on the right side. If we use our exponent rules, we can remember that we can write that right side as 5 to the 2x. We can actually multiply those exponents together. Now that I've done a little manipulation on this, I do have it written as base to a power is equal to same base to a different power, which means I can go ahead and equate those exponents. Writing this as x minus 1 is equal to 2x. I'll subtract x to get my x's together, and I get negative 1 is equal to x, solving my equation. So here are the two techniques that we can use. One is taking the natural log of both sides of the equation. This one works really well, especially when we have an exponential piece on one side and we have a number piece on the other side. And then we have this other technique of trying to write our two exponentials with the same base. If we can do that, then we can equate the bases and go from there. All right, now that we've seen these two techniques, let's go over to the next video to try these techniques in action in a variety of problems.